we move on further, once we know the process, the input variables, the output variables, disturbances, manipulated variables, we now come to the design element of control systems. So we have a system and we want to control it, and we had enough deliberations on why we need to control the process. Now we come to how to control the process, a chemical plant, for example. So when you're going to design the elements of a control system, we have to look into the next basic questions which we must ask, and not only ask, we should try to answer, so that we can design a control system that will satisfy the control needs of a chemical process. So what are those questions? We will ask 5 different questions one by one, maybe in the sequence that is desired. It can be out of sequence also, but anyway. So the first question is that what are the operational objectives that a control system is called upon to achieve? Before we design any control system, we see why are we going to go in for that, what are the objectives. Again, we have already discussed objectives. They can be, again, I'm repeating once again, ensuring the stability of the process, or suppressing the influence of the external disturbances, or optimizing the economic performance of a plant, or it can be combination of the above, one of the two, three, any of these. It can be any one, it can be any two, it can be all three. So depending upon that, we will design the control system. This is the first question which is required, and we have already gone in for long discussions on this in the previous sessions. The second question, or the next question, is that what variables should we measure in order to monitor the operational performance of a plant, how the plant is performing. So it's very evident that we'll try to monitor directly the variables that represent our control objectives. And what is done, this is what is done whenever it's possible, and these measurements are called primary measurements. Wheresoever we cannot get anything from the primary measurement, we infer it from the secondary measurements, and we will talk of these secondary measurements a bit later. But whatsoever the primary measurements which we can do, for example, we have again CSTR. You want to know what's the temperature, what's the height, and so on, inflow, outflow. These are the primary measurements which we will be going in for to know the performance, to know the operational performance of a plant. So we should go in for getting those primary measurements done. Now, as I've already said that some of the measurements cannot be done directly, so we cannot get the measurements. So we go in for the secondary measurements, we get the supporting measurements as such. So these supporting measurements are somehow able to give us some estimate of the measurement which cannot be made. We want to measure the output, we cannot measure the output, so we'll be making the secondary measurements, and we will be defining some mathematical function from where we can infer the unmeasured output. So this is what we will be seeing, how this can be done from empirical, experimental, or theoretical considerations. This is something we'll be seeing later. Next question which comes to our mind is that what are the manipulated variables to be used to control a chemical process? And here again we come back that I want to control the level of this tank. I can control it. I have the options depending upon the process. I can either control the level by controlling the inflow, or I can control this level by controlling the outflow. When I control the outflow, this outflow becomes the input variable. So these are manipulated variables. I can manipulate this variable, I can manipulate this variable. I want to control the temperature, I can manipulate this variable. I cannot manipulate this, but it's easy to manipulate this variable. FC is the flow of the coolant. I can put a value over here, put a valve over here, and that valve I can adjust, close it or open it to control the temperature of the jacket, which in turn is going to control the temperature of this liquid inside the stirred tank reactor. So this is what you have to see. You have to identify the manipulated variables to be used. And so according to that, we will be going for the design of the control system. And the next question is that what is the best control configuration for a given chemical process control situation? This is something we will be deliberating upon to a bit greater extent as compared to the rest of the questions which we'll be asking. We have already asked three questions. This is the fourth one. The fifth one we also asked. This third question, this fourth question is perhaps carrying the most weight. What is the best control configuration? What do you mean by configuration? Again, we will study this in 2 3 slides coming thereafter. Now, first of all, we have to we have to identify whether our process is CISO or it is MIMO. What is the meaning of CISO? CISO means, as you can see from here, CISO means single input, single output. It's a simple thing. There's no interaction as such between the input and the other inputs. If I might be there in the neighboring inputs, but they are not interacting, so we still call it as single input and single output system in a CISO system. Or you can have MIMO. MIMO means multiple input and multiple outputs, where you have large number of inputs and large number of outputs, and one output is affected by large number of inputs, so it's a lot of interaction is taking place. So you cannot say that two CISOs will not make one MIMO. If you have two CISOs, like you're controlling the temperature of the tank and you're controlling the level of the tank, but the level is not affecting the temperature to much extent, and the temperature is not affecting level to much extent, minor interactions may be there which can be neglected. So we'll say we have one input and one output. Input is the flow rate and output is the level. You have one input and one output. Again, input is the flow rate of coolant in this case, and output is the temperature. So these two, because it's a jacketed system, the flow of coolant is not going to affect the level, and the inflow is not going to affect as such the temperature is you can see there. So you have two CISOs, but as such, if we consider one loop, only one loop at a time, and we consider only temperature or we consider only level, so we call it the system to be CISO. And in case there is an interaction, like for example, if the inflow is also affecting other than level, it's also affecting the temperature, and the temperature is controlled by directly injecting some steam or directly injecting some hot water into it, so that is also going to affect the level. In that case, it will become a multiple input multiple output system, because the two inputs and the two outputs are all related to each other. We will have a very large discussions on it in the subsequent courses, where we will be discussing the interacting systems. But for the time being, to keep the things short and simple, we will be mostly focusing on CISOs. Although we do have MIMOs, practically everything is a MIMO, but we neglect the interactions and we consider only CISOs, one CISO at a time, one single input single output system at a time. So here we have, I've already given you the cases of steam flow rate and the effluent flow rate, changing both the level and as well as the temperature, so that becomes a MIMO. Otherwise, if we take it only input and output and only flow rate in flow rate out, determining the level, there's no change in temperature, or we don't consider the change in temperature at all, so in that case it will be CISO. So as once again for the last time, I'm saying that from now onwards mostly we'll be considering only CISO. So this is the first thing we have to take into account as we are going to select the configuration, the control configuration. There are three more things to go. We will be considering all these three more things to go one by one. The configuration, once we have considered it's a MIMO or a CISO, in this case in the figure we are seeing MIMO. What we see is that you have manipulated variables, and we start with the process. This is the process, and this process is getting affected by the manipulated variables, and it is giving out the measured outputs. And these measured outputs is the focus is on measured. The term is measured. The outputs are measurable, so we compare these outputs with the set point, that what should be the temperature, what should be the level, what should be the concentration, and so on and so forth. And the controller takes the action, it manipulates, it changes the manipulated variables in a controlled manner so as to bring about and the changes in the measured output which may be getting disturbed on account of the presence of these disturbances which are acting on the process, which are giving some outputs, and these outputs are measurable outputs, and we take a feedback from the measurable outputs and give it to the manipulated variables. The unmeasured outputs cannot be used as a feedback. Feedback is always in terms of the measured outputs. So this is generalized MIMO system which we go in for a kind of feedback control system. We will take one practical example in the next slide. So this is the case of a distillation column, and in this distillation column what we are going to do is we are going to see the output which is going out as a distillate. We are going to get the composition analyzer, see the concentration or the composition of the system, whether it is matching with the set point or not, and according to that, whether it is there or not, we open or close the amount of reflux that is going back into the distillation column to bring about the desired composition. So if the composition is up to level or it get changed accordingly, this reflux is slightly opened or slightly closed. Here the system is based on the fact that this composition analyzer is able to measure the output. The output is measurable, and only then you're going to get the feedback, and that feedback is it's going to the manipulated variable. It's going back to the manipulated variable, and this is the process which is happening over here. So this is one simple example of the feedback system, and we have more systems to be seen in the subsequent slides. This is an inferential control system, and in inferential control system, once again you have a process as usual, and you have the outputs. These are the outputs which need to be measured, but somehow these outputs cannot be measured directly. These cannot be measured directly, so you don't have to measure it from the primary measurements, but rather you have to estimate it from the secondary measurements. As we had saw earlier, you have to estimate it. The estimator is able to measure these outputs. These are the secondary outputs from where we are able to estimate the value of the control variable, which is primarily unmeasured, unmeasurable, but we get its value, and those values are compared with the set point. It goes to the controller, it's compared with the set point, and it decides how the manipulated variables are to be changed so that the output which was not directly measured but was able to give us the estimate of through secondary measurements, because we are inferring the output, so it's called an inferential control system. And again, here the objective we have taken is that the disturbance is going to change the process, and we are going to suppress this change with this objective. And this is the theoretical MIMO generalized process for the MIMO. But if you go in for CISO thing, practical thing, in the next slide you'll see how we are going to control the system using inferential control system. So here we have again the process, and we are going to control the reflux, but this composition is not directly measurable, so you cannot take the feedback from here and give it to reflux control valve. So what we do is that we cannot get the feedback directly, so we measure these secondary variables. T1, T2, T3 are the secondary variables. They go to this computer, and that's going to measure the, or you can say it's going to estimate, it's a estimation of the concentration which cannot be measured directly, and that goes to the control point, and that's going to control the reflux as it was in case of feedback, with the difference that in feedback we were directly measuring the composition. In this case it's not directly measured, it's measured with the help of these secondary variables, the temperatures at different points, and it's going to estimate the concentration or the composition of the distillate, and according to that it's going to control the reflux valve going, part of it goes to the distillation column and part of it goes out to the distillate as such. So this is the practical example of inferential control system, and this is the third configuration and perhaps the last one as you're going to discuss in this as an answer to this question, that this is the feed forward control system. What we do in feed forward control system, again you have a process and you have some disturbances taking place, but feed forward control is possible only where the disturbances are measurable. You are able to measure the disturbances. So these disturbances are measured and its effect on the process is again anticipated. It's going to change the process, but before it changes, before the process goes haywire or its output is disturbed, this controller is able to judge what is the going effect of this disturbance on the process. So this controller is going to manipulate the variables, which are manipulated variables, such that the effect of disturbances is countered by, is negated by, is equal and opposite to the effect of disturbance. So the net process change in the net process, or you can say change in the output, is nil. There's no change. The process is not affected. We don't take any feedback. We don't measure this feedback because we are quite sure that we have taken the action and all the effect of disturbance is countered by the manipulated variables. So these measured outputs, they go as such in the controlled form. You may measure it for your own satisfaction, but actually it's not used for control. So before the disturbance acts upon the process, we take the control action before it acts. That's why it is called feed forward control. It's not called feedback, because in feedback the action takes place after the damage is done. Here the action is taken before the damage is done. That's what it's called feed forward control system. So this is the fourth question which is answered while designing the elements of the control system as such. We have to see whether it's a MIMO or it's a CISO, and then we have to go in for, depending upon the situation, whether we have to go in for the feedback system, or we want to go in for the inferential system, or we want to go in for the feed forward system. As the things may be, we will study all these in detail, and the complications and the advantages and the disadvantages of each configuration, as the case may be, will be studied in detail. But this is the beginning of the system as such, of this interesting, very interesting course, as you might be finding it by now. And the design elements of control system, they consider into account the configuration of controller in one of these three basic forms. So this is the practical form of feed forward control system. Again, see, this is the process, and in this process what we see is that whatsoever is the input feed and the disturbances in the input feed, if at all there is any change in the input feed, so before the input feed change is able to disturb this distillation column, and it's going to change the composition of the distillation column, instead of taking feedback from after the change happened, we take the feed forward, means we measure the disturbance itself, and we continuously analyzing the feed composition, and any change in feed composition the controller is able to sense, and it's able to also see that how this can be countered by changing the reflux amount going in is also changed, it's increased or decreased, so that by the time the effect of feed on the column is there, the effect of reflux is able to negate it, it's able to cancel it, and the output goes at the same composition level as it was, since we are measuring the disturbance before it is acting, before it is entering into the system. That is why it is called feed forward control system. This is what is the practical example of feed forward configuration, as we have discussed earlier. So the last question is that we have taken information from this entire process. So how are we going to adjust the values of manipulated variables? See, in this course, you will be studying in detail something called on-off controller, something called proportional controller, something called proportional and integral controller, or it's called PI controller, and something called proportional, integral, and derivative control, that's called PID controller. Some of these things you might have studied in some other courses like control systems, or you might be studying in parallel right now. So this P or PI or PID, proportional, integral, derivative, which of the two is to be used, which of the three is to be used, or you can say which of the four is to be used if you consider on off also as one of the configuration, then if at all we have chosen P, then what should be the value of P? Proportional gain. If you're using Pi, what should be the value of P in that case? What should be the value of I, integral time, in that case? We will study all these things in detail later, but right now, to give you an idea, let us say again we have continuously stirred tank reactor, or we have the heater, whatsoever of the two you want to see. And what we see is that the inflow temperature, it increases. The inflow and whatsoever is the reactant going in or the feed going in, its temperature suddenly increases at T is equal to 0. Let us say it becomes from 30 degree, it suddenly becomes 40 degree. Suddenly, it's a step change. It's a continuous, it's you, as you can see over here. Then what will be the effect on the temperature on the output? If left uncontrolled, what will be the output? If we go in for P controller and we change the gain of the P, we slowly and slowly gain is increased, and what will be the effect? So all those things, they need to be actually measured, actually simulated, actually calculated or determined through the theoretical values. We will not be discussing how it is done because it's too early at this stage, and anything anyway, these things will be done in detail later, so I'm not going to give you the details of that. I keep it, reserve it for the later discussion. Let us see one by one. The case of a P controller, as you can see, in case I do not apply any proportional control, that is the gain of the proportional control is set to be 0, then as there is a sudden change in temperature in the input, the output also changes, it increases, it goes on and on and on, and somewhere over here naturally it settles. This is the uncontrolled stuff over here. The change from the steady state, the output, it increases and settles at this point. But the advantage of going in for proportional control is that in case you have some control, then the steady state will be nearer to the steady, the final element will be nearer to the final temperature, will be nearer to, relatively nearer to it. It's quite far off from the steady state. The deviation will be there but will be lesser, and if I increase the gain, the deviation will be still lesser, and so on and so forth. So this is the effect of proportional control. This is what we see, that can I tolerate up to this point, or should I be happy when I'm getting a response like this? So in that case, I'll be using P controller with its this is the gain of the P controller. Suppose I'm not happy with this is called steady state error. The error which continues to be there, it's called steady state error. I'm not very happy with this, so I have to change the configuration. Instead of P controller, I will be going in for PI controller. How it happens and why it happens and to what extent it happens is something which we'll be discussing in later stage. But let's see, if you're not satisfied with this P controller, I want to go in for PI controller, then what will be the response like? This is when it is PI controller. Once again, we start with when there is no control, then it is this is the stuff. But in case I go in for PI controller, and in PI controller with one set of the gain, I'm just having a composite gain as a PI, as alpha dash I taken it to be equal to 1, then in that case it's going to settle down, but it's going to settle down with some oscillations. And after some time, if I increase the gain, then what's going to happen is that these oscillations will be smaller, and it's going to settle down a bit quickly. And in third case, in third kind of configuration, alpha dash as we call it, it's going to settle down quickly without any oscillations. So depending upon which of the three, obviously in all three I find this configuration to be the best, so I will be choosing. If I'm happy with this, then I will be going in for more complicated calculations or more complicated controller. Instead of a simple P controller, I will go in for PI controller with these properly tuned values, as we call it. We properly tune it so as to get this response. So this is again one of the design element of the control system, which configuration, and again in which configuration. It's the feedback configuration. And feedback configuration, what should be the values of the control elements as such in the feedback. Again, if we could go in for P or PI, or what kind of the design parameters of Pi should be there. The gain of P, the gain of I, how much it should be, they properly tune it, and that's how we get the results. So these are the 5 questions we have to ask, we have to answer As such, we have seen one by one to go in for proper designing of the control system, or these are the design elements of control system. Hope you have enjoyed this part of the learning as well. And in case you have any queries, your doubts, or you have any observations, you want to share something with me or ask something from me, you can always contact me through Zoom or WhatsApp, or make a direct call or have a face-to-face interaction as the case may be. And I hope you have now learned a little bit more about the controls and the control systems. I thank you for being with me, and I wish you a safe stay. Enjoy learning. Bye bye. So, this is the practical form of feed forward control system.